Okay, so here we are in number 5. We're finding the values of x and y. And so we notice these two triangles, this triangle and this triangle, are similar triangles. How do we know they're similar triangles? Well, we know these two angles here must be equal angles because they're diagonal. They're called vertical angles. They're diagonal. They're always equal. So, and then, of course, they're giving us this angle and this angle are equal. So that's two equal angles in the two triangles. And so that means that actually all three angles have to be equal. And so the two triangles are similar by angle, angle. All right, so now that we know these two triangles are similar, what we can do is we know the sides are proportional, equal fractions, right? So now the trick is, though, we got to match up which one goes with which one. So like this x here, he corresponds with which side in the other triangle? Which one does he match up with? Well, look where he's at in the triangle he's in. His side here is between the double mark, this double mark here, and the spot that has nothing. So which side in this triangle is between the double mark and the nothing angle, the angle with no mark at all, the 28. So see how the x corresponds with the 28? So x is to 28. All right, that's our fragment. In fact, let me write it up here, get a little more room for everything. So x is to 28 as, now what are two other sides that are corresponding? Well, say like this, 15. Between the single and the double marks, single and double angle marks, must correspond with the 20 between the single and double angle marks in the other triangle. 15 to 20. See how that works? So I started with a small triangle. So I did the small triangle on the top and the big triangle on the bottom, didn't I? And I did x to 28, 15 to 20. So there's our two equal fractions. Let's go cross multiply. 20x is 15 times 28. And what is 15 times 28? It's 420. Using my calculator. This is 20x. Last step to get x alone there. We get a divide by the 20. And so these cancel out, and so x equals 21. So x must be 21. Now, to find y, it's similar. Y between the single mark and the no mark angle must correspond with 9 between the single mark and the no mark angle. So y is to 9. Now, notice I'm starting with the big triangle. You don't have to. You could have started with the small. But I happen to start with y, because I just went right to that letter we're trying to find here in the second part. And so I started with y. So I started with the triangle on the right. Started with the big triangle. So I'm going big triangle over small triangle. So y over 9 is what? I could go 20 over 15. Do you see that? Because the 20 and the 15 correspond, and the y and the 9 correspond, right? The 20 and the 15 are between the double and single angle marks, double and single angle marks, so they correspond. And I'm starting with the triangle on the right, the big triangle every time, y over 9, 20 over 15. You could do it upside down. You could go 9 over y is 15 over 20, and that would work just as well. It doesn't really matter. Just be consistent. So, right, if I'm starting with the small triangle in the first fraction, then I've got to start, right, the 9's the small, then I got to start with the small triangle in the second fraction. Over here, I happen to start with the big triangle in the first fraction, so I got to start with the big triangle in the second fraction. Just be consistent, and it'll work out. All right, now we cross multiply. These two multiply. 15 times y is 9 times 20. So 15 times y is 180. Last step to get y alone, divide by the 15, and so y equals, using my calculator, 180 over 15, 12. So y must be 12. So there we go. There's how we solve for similar triangles in those two triangles. All right, on to number 6. A photocopy of a polygon was reduced to 10% of its original size. 10% of its original size. Then the copy was again reduced to 10% of its size. First question, is the second copy similar to the original? So we had like an original, and then the new one was like only 10%. It's a lot smaller. 10%. So this is the original. This is the first copy, and then the second copy was like so small you can hardly see it. Just make like a little bitty one. And this is the second copy, which is 10% of the other one, of the one right before it. All right. So is the second copy similar to the original on that? Yes. Yes, because the angles stay the same and the corresponding sides are proportional. Yeah, of course. Whenever you make copies, you shrink or expand, you're getting a similar copy. It's a similar shape. Okay, then B. What is the ratio of the corresponding sides of the second photocopy to the original? So, the ratio, they want the ratio of the second copy to the original. They want second to original. The ratio second to original. Well, this is the first copy is 10% is big, right? Because a 10%, yeah, I just changed that to a decimal, so it's 10%, which, remember how to change a percentage to a decimal? You just move the decimal back 2 places. So the decimal's here, and it goes 1, 2 back. So it ends up right there. 0.10, that's the decimal version of 10%. Okay. It's 10%. And then we do it one more time. We do another 10% of 10%. So you just take 0.10 times 0.10 again. And that's 0.01. So the answer is 0.01. The second copy is 0.01 of the original. Oh, and they say 4 decimal places. So how do you do 4? It's just 01. Well, you add 2 zeros in the back. That way you've got 4 decimal places, right? You can always add zeros at the back. That doesn't change the number. And they wanted 4, so okay, we'll just add 2 zeros in the back. So it's really just 0.01, but we added 2 zeros in the back, which doesn't change anything for their 4 decimal places. So you see how we got that? If you have an original, you make a copy that's 10%. That's a decimal 0.10. It's 0.10 of the original. It's 10% of the original. 1/10 of the original, 0.10, and then you do it again, so it's 0.10 times 0.10. Every time you do a 10% copy, you just multiply by 0.10, and that equals 0.01. I'll just move it over there. That equals 0.01, and that's our answer. All right, let's try number 7. Sketch 2 hexagons with corresponding sides proportional, but so that they are not similar. So sides are proportional but not similar. See how these sides are all the same? It's a regular, right? All those sides are the same. Same thing here. All these sides are the same. So that's proportional. All those sides are equal, right? All those sides look exactly the same as all these sides. If I go over here, as these sides over here, they all look exactly the same. but they're not similar, right? These are not similar. Why are they not similar? Because their angles are not the same. Remember, two shapes that are similar have to have equal angles and sides that are proportional in the same ratio. They certainly have sides that are proportional, but they're not similar because their angles are not equal. Why are the other answers wrong? Well, let's take a look here. These two are actually similar, right? They're the same shape. They're in fact identical. They're congruent. I shouldn't just say they're identical. They're congruent, right? You just turn this one, just flip it to its side, and they're the exact same shape. Same thing with these two. These are congruent. They're exactly the same. So therefore they're for sure similar. They're even more than similar. They're congruent. They're identical. And then these two are definitely similar. One's just a bigger version of the other. So A is the answer where they're not similar. Okay. Now number 8 here. Well, this one's pretty tricky. Let me try to help out. It's especially tricky because they're making us do a bunch of fractions. So here's the idea. The first copy, you copy a page and get on a machine at 73%. So you make the thing 73% of its original, right? You shrunk it down a little bit. It's 73% as big as its original. Okay. What is the corresponding setting to obtain the original? So you want to go back to full size. So what if you just made a copy at 73%, right? It's a little smaller than the original image. And now you decide, oh, you know what? I want to go back to the original size. I'm going to go back to the original size. What do you set the machine on? What do you put the photocopy machine on to take this 73% image and expand it to go back to the original? In other words, 73% times what percent? Remember, so whenever we do like another copy, you're just multiplying. That's what we did back here in number 6, right? We did a 10%, which decimal is 0.10 for the first copy, and then we did a second copy, which is another 10%, another 0.10. We did 10% and then 10% again, 0.10 and then 0.10 again, and it made it 0.01. That was the decimal. Same thing as 1%. It made it 1% of the original of the original. So anytime you copy and then copy again, you just multiply the decimals or the percentages or the fractions. It doesn't matter on that. You just multiply them together. So 0.10 times 0.10 made 0.01. 0.01 is after 2 copies. That's the second copy. It's 0.01 of the original, or 1% of the original. Well, on this one, it's the same thing. The first copy is 73%. What should we set the second copy at? What percent to equal what? 100%, right? We want it to go back to the original. We're saying first copy, 73%. Second copy, what? To equal the original, to go back to the original, 100%. So we got to figure that out. Now, if they would let us just do decimals, or just stick with percentages straight, decimals basically, decimal percentages, this wouldn't be that bad of a problem. But see down here they say, we want all fractions, please. Fractions and mixed numbers and stuff. So it makes this problem hard. Because the basic idea is not bad. Just 73%, that's the first copy, times what percent setting on the machine will take it back to 100%. Anyway, we got to do it as fractions. I'll quit complaining. Here we go. So how do you change 73% as a fraction? Well, it means 73 per 100. Do you remember that from Math 10A? That's what percent means. When you write 73%, the percent symbol, percent means 73 per 100. Remember, a century is 100 years. A cent is 1/100th of a dollar. Cent is the word for 100. So percent per 100, it's 73 per 100. That's why the symbol has 2 zeros with a dividing bar in it. It's telling you divide by 100. So 73% is 73 per 100. And X percent, is times in the middle here, is X per 100. And 100% is 100 per 100. right? Each of those numbers divided by 100, because they're all percentages, they're all per 100. We got to change to fractions. It's kind of weird having this all in fractions instead of decimals. I wish they didn't do that, but I guess it's good practice for fractions because they want a mixed number answer. All right, so how are we going to solve that little equation for x? Well, first off, let's just make this 1, right? 100 divided by 100 is just a nice clean 1. So what do we have here? Let's just multiply top times top. 73 times x is just 73x over 100 times 100, that's 10,000 equals 1. Okay, now how do we solve that for x? We're trying to get x alone. So multiply by the upside down. Multiply by 10,000 over 73. And whatever you do to one side, you have no choice but to do the same thing to the other. So then the 10,000s cancel, the 73s cancel, x is alone. Bring it up here. X equals 10,000 over 73. Now, that's a big, ugly number. So what you're going to have to do is divide on your calculator. If you divide on your calculator, and I'll do it right now on my calculator, you get 136.986, blah, blah, blah. We'll take the one thing, we need to give a mixed number. See, if we could just give a decimal answer, that'd be it. We'd be done. But they want a mixed number. So we got to say, okay. So the answer is 136. That's the whole number part. And then some kind of fraction. And you know the bottom is 73. How do you know? Well, the denominator doesn't change. When you change from an improper fraction to mixed number, it's the exact same denominator. So we now know the whole number in the front is 136. It's 136 and something over 73. How do we find that? Well, basically we're long dividing 73 into 10,000. That's what this fraction means. 73 into 10,000. And we know it goes in there 136 times because that was the whole number. So just take your calculator and just multiply 73 times 136 now. And what you'll get is, this times this, you're going to get 9,928. Subtract those and you get the remainder of 72. So that's what must be left here. This must be 136 and 72 73rds. That's the same exact number as 1,000 over 73. It's just 10,000 over 73. That's just kind of a real pain because of those mixed numbers. I'm not going to probably make you do mixed numbers that bad on the test. That was a rough one. All right, on we go with, there's 8 again. We already got it. So number 9 now. A student wants to know how far above the ground the top of a leaning flagpole is. So whatever, blah, 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 blah. So X, how far above the ground. So that's how far above the ground. So this flagpole right here is leaning. It's the leaning tower of Pisa. It's the leaning flagpole. And we want to figure out how far above the ground it is. Well, you go straight down to the ground. That's how far above the ground is. That's X. That's its height. I want to find that. So how do we find that? Well, do you see that we have similar triangles? We have this big green triangle is similar to this little purple triangle. They're the same shape. One's just a bigger version than the other. How do we know? They both have a right angle, and they both share this angle here, the lower left corner. So they have two angles the same, so they really have, therefore, all three angles the same, and they're similar triangles. Okay, great. So we know they're similar triangles. What does that mean? Well, that means we can set up a ratio of their sides. Their sides are going to be proportional, equal fractions. So let's do it. First off, notice that this is in inches, and they want the answer in inches in the end. So let's get everything else in inches. So 2 feet, this is going to be 24 inches, right? Because there's 1 foot is 12 inches. Remember that? So I just took this 2 feet and multiplied by 12 inches in each one of those 2 feet to get 24 inches. for this piece here. And then 7 times 12, this is 84 inches. So let me recopy the figure over here so we can see it a little bit better. So we're saying, okay, this is 24 inches. This is 11 inches. Well, I don't need to write inches. It's all inches now. It's 11 inches. And then all the way here, that's at 84 inches. And we're looking for x. Okay. So, remember what we do. We set up a ratio from the big triangle to little. So, x is to 24. X is to 24. As, right, the right side of the big triangle to the right side of the little, as the bottom of the big triangle, 84, is to the bottom of the little triangle. That ratio's got to be equal. Cross multiply. 11 times x is 24 times 84. Use your calculator. I'm not sure what that is. I'm getting 2016. And then last step to finish solving for x, divide by 11. And I'm getting x equals 183.2727 blah blah blah, and they say round to the nearest inch, so we'll say 183 inches. That's rounded to the nearest whole number of inches, 183. 183.27 rounds closer to 183 than it does to 184, right? So there it is, rounded to the nearest whole number of inches. All right. Oh, we could have done it up there. I didn't see that. Okay, so number 10. Let's go to number 10 here. Find the distance D. Cross the river. So we got this D. So we got, you can just look at the picture. We have similar triangles here. Similar triangles. And so let's set up a ratio. So first off, how do we know they're similar triangles? Well, this angle and this angle, diagonal angles called vertical angles, have to be equal. And then right angle, so that's two angles, so therefore the third angles have to be equal, and the two triangles are similar by angle. Okay, so now let's set up the ratio. So D, what we're looking for, D is to what? So what does D correspond with? With the 300, huh? Because the D is between the right angle and the angle that has no mark. The right angle and the angle that has no mark, that's the 300 over there. So the D corresponds with the 300. D is to 300 as 120 is to 50, huh? Because they go together, don't they? Between the right angle and the single mark, between the right angle here and the single mark, that's the 50. So, and I went big triangle to little every time. D is to 300 as 120 is to 50. So there's my two equal fractions in similar triangles. Multiply, multiply, cross multiply. 50 times D is 300 times 120. 50 times D is, what's that, 36 and 1,000. And then last step to finish solving for D, divide by 50. So D equals 720. So D must be 720 feet. Good. All right. On to number 11. Good on that one? Let's go on to number 11. Are the given quadrilaterals similar? Tell why or why not. Well, looks like, so there's this and this. Are they similar? What does it take again for two shapes to be similar? All angles must be equal. Sides proportional. The angles have to be equal and the sides proportional. Are they in this case? I think not. I think 8 over 12, does that equal 12 over 19, right? They would have to be in the same ratio. I went from this little one to the big one. 8 to 12 and 12 to 19. I don't think those are the same fraction. Divide this one on your calculator, you get 0.6666. And what is the other one? 12 divided by 19. It is a 0.63157, blah, blah, blah. So the answer is no, they're not equal. Remember that the fractions, the ratio of the sides have to be equal, proportional we call that. They're not. So the answer is no, because not all the lengths of the corresponding sides are proportional, and or not all the angles. The angles may not be also, I don't even know, but for sure the sides are not proportional. So there we go. Number 12, draw similar but not congruent isosceles triangles. Similar but not congruent. Similar but not congruent. Okay, so how can we do that? Well, the answer is going to be B. These two, first off, it's isosceles. Yes, these two sides are equal, and see how the triple and the triple are equal? But this side is different. He's a double, and this side is a 4, so he's different than the other two. Like that. So they're both similar isosceles triangles. Now, how do we know that the other ones are not? Well, on part A, they never put a right angle in here. Otherwise, it would be good, right? Part A is basically, but they never actually put the box in the corner, so we don't know that's a 90-degree angle. So we don't know that those have the same angles. Remember, to be similar, we've got to have the angles the same. So that's why it's not A, because they didn't put the box in the corner there. We don't know the angles are the same, whereas here they did, right? Corner, it's got same angles. So side, angle, side, angle, side, proportional, not equal, right? Proportional. Now, the other two triangles, C and D, are not the answer because these are identical. These are congruent, not, right? And they said not congruent, right? They're identical. How do we know? By side, angle, side, angle, side, right? Because this single mark and this single mark means those are exactly equal. And this single mark and this single mark, those are exactly equal, not just proportional. Whereas ours here are proportional, right? 1 is to 3 as 1 is to 3. They're not equal, they're proportional. So those are similar. Whereas these are congruent. Same thing here. Side, angle, side, angle, side, congruent. So that's why those are not the answer. And then A was missing the right angle mark. So there we go. Its answer is B. A little tricky there. All right, so number 13. These are the ones we're supposed to go through and prove similarity. So why would this triangle be similar to that triangle? Well, do you see how the sides are proportional? Right? If I take left side to left side, 2 divided by 3, I get the same thing as right side to right side, obviously, 2 divided by 3, which is the same as bottom to bottom, is it? Is that the same ratio? If you divide that in your head, you get 0.6666, 0.66666. If you divide 1 by 1.5, you get 0.6666. Yeah, they're in the same ratio. So then that is by side similarity. So the three sides aren't equal to each other, but they're in the same ratio. Side similarity. Okay, and then what's the scale factor? They want ABC over triangle DEF. ABC, so that'd be the 2 over the 3. You just take one side over the other. 2 over 3. That's that 0.6666. Same ratio all the way through, right? Even 1 over 1.5. But that's not a simplified. We don't want decimals in the middle of fractions. That's not simplified. So 2 over 3 is the scale factor of the small triangle to the big one. The small triangle is 2/3 as big as the big one. Now, part 2. So same kind of thing in part 2. Here we're going to have side, angle, side, angle, side, which connects the which makes the little triangle and the big triangle similar. Now remember, the sides aren't equal. This isn't congruence. This isn't side angle side congruence. They're not identical. Remember, we had a side angle side theorem for proving two triangles are identical. These are not identical. They're similar. Because the sides, in the side angle side, the sides aren't equal. They're proportional. Let's prove it. So the 3, notice, goes with the 6. It's right. The 6 is twice as big, and the 5 with the 10. The 10 is twice as big. So you see how it's the same ratio. 3 over 6 is 5 over 10. Same ratio. They're both a half. It's 0.5 if you want a decimal, or it's a half if you want a fraction. They're in the same ratio. The sides are in the same ratio, and the angle in between, the right angle, are equal. So by side angle side, and what is the scale factor of the small triangle, triangle ABC, to the big one, triangle EDA? Well, it's 3 over 6, which reduces to be a half. The scale factor, right? If you reduce any of those fractions, if you divide top and bottom by 5, you get a half, or divide top and bottom by 3 on this one. Either way, you get a half. That's the reduced fraction, simplified fraction. There is a half. Part 3 is the little triangle here and the big triangle. Are they similar to each other? And if so, why? Yeah, see how they share the double angle here, and we know they share this angle because the lower left corner is the same angle in both triangles. So they have 2 angles the same, so which means all 3 angles are the same, and they're really similar triangles. So by angle, those triangles are the same. Now, what's the ratio of scale factor of triangle ABE to triangle ACD? ABE is the little, so that'd be the 6 is to the big. Now the big triangle, ACD, there's the big one. So the bottom of the little triangle is 6. The bottom of the big triangle is 6 plus 2, 8, isn't it? 6 over 8. Okay, and then you take that 6 over 8 and you got to reduce the fraction because they want simplified fraction divided by 2 top and bottom, 3/4. So the little triangle is 3/4 as big as the big triangle. That's the scale factor. Finally, part 4 here. Why are these two triangles similar? They share this angle, because those are diagonal angles called vertical, and then they share the 45. So that's 2 angles that are the same, which means all 3 angles are the same, which means they're really similar triangles by AA. Now, what's the scale factor? Well, they want triangle ABE over triangle DBC. So the ABE, start with the 1 on the left. The 3 is to the 4. There it is. 3/4. So the one on the left is 3/4 as big as the one on the right. They're the same shape. The one on the left is just 3/4 as big. All right, number 14. Here's another similar triangle situation. To find the height of a tree. So we have another. So here's some kind of tree. There's a shadow at the top of the head. So basically, here's the tree. This is our X. We're trying to find that X. Notice they're playing around units on us. So they want meters in the end. So we've got to convert everything to meters. This is meters, but this is centimeters. Now, do you remember the conversion between centimeters and meters? Maybe you're not aware of that. Let me help out with that. 150 centimeters. If you want to change that to meters, you got to divide by 100 because there's 100 centimeters in every meter. That moves the decimal back 2 places. That's 1.5 meters. So this is 1.5 meters. All right, so now we can set up the equal fractions. We can go right side to right side. So X is to 1.5, or here, let me move it up here. X is to 1.5 as 33 is to 3. No, that's wrong, actually. Now, that's a really common mistake. If you set it up like that, that's actually going to be wrong, but it's a really easy mistake to make. A lot of students make it, so I want to help with that, so I did it wrong on purpose. Now, what's wrong with that? Why is that wrong? Doesn't that look good? X is to 1.5 is 33 is to 3. No, do you see the problem? We're only supposed to take sides of the triangles, whole sides, not parts of sides. 33 is not a whole side. Look what 33 is. Can you tell by this little diagram? 33 goes from here to here. It's this. In other words, it's only part of the big triangle's bottom. It's not the whole bottom of the big triangle. What is the entire bottom of the big triangle? 33 plus 3, 36. 36 is the bottom of the whole triangle. 36. Let's change this. 36 is the bottom of the whole triangle. So now it's good. Now we're going right to right, bottom of the whole to bottom of the little. Right? 36 to 3. So now it'll work. So now we can cross multiply. So we get 3 times x is 1.5 times 36. So that's, what is that, 1.5? I think it's 54. And then divide by 3. X is, what's that, 18. So x is 18. The tree must be 18 meters high. So you can actually measure a tree, the height of a tree, in that way. You see how that works? We could actually measure the height of a tree that way. That's a good way to do that. Okay, number 15. Are all semicircles diameters not included, similar to each other? Are they all similar? So what's a semicircle? That means a half circle. Semi is half. Whenever you have semi in front of a word, it means half. So a half circle. So if you have a little half circle and a big half circle, are they similar? Are they well, it's hard to tell with my circles because they don't look similar. So if you take a little half a circle and you take a bigger half a circle, are they similar to each other? Yes, all semicircles have the same shape, right? If you take the little one and you blew it up, it would fit right on the big one, right? Take a little circle and make it bigger, it'd fit on a big circle, or half a circle, same thing. Same, yes, they're similar. Right, all right, let's move on. Are any two cubes similar? Like, so if you have a little cube and then a bigger cube, are they similar? Like if you took the little one and you expanded it, would it blow up to exactly fit on the big one? Are they the same shape except for size? Yeah. Any two cubes are similar because all the faces are squares, right? They're all squares. And the dihedral angles, that's the angles between the sides, like the angle between the right side, the right side and the base there is 90 degrees, measures 90 degrees. This one says they're similar, but the dihedral angle is 45. It's not 45. This right here is a 90-degree angle, the dihedral angle, the angle between the two faces. All right, number 17. Write a description of what it takes for two prisms to be similar. So remember what prisms are? They have two faces that are the same. Like maybe the top is a triangle. Or here, let me draw it this way. The top and the bottom are triangles, for example. Right? That's a triangular prism. So prism have the top and the bottom being the exact same shape and then straight sides in between. So what's the story here? Yes, two prisms are similar as long as their bases are similar, right? The bases, the top and the bottom, would have to be similar, right? So like if you had a small triangular prism, and then over here, let's call that the big one, and I'll make a small one over here. Right? Are these two shapes similar? If you blew the little one up, would it match onto the bigger one? Yes, as long as the bases are similar, right? These two bases need to be similar shapes, and all the lengths of the corresponding sides are proportional. That's what it takes. Let's go to number 18. If two isosceles triangles have non-base angles of 40 degrees, are they similar? So isosceles triangles. So like a triangle like that, and maybe a bigger one like that. Isosceles, two equal sides. Non-base angles of 40. So these are the base angles down here. Okay? And if this is 40 degrees and this is 40 degrees, those are the non-base angles, right? The top angles, in other words, not the two at the bases, are 40. Do those two isosceles triangles have to be similar? Well, do we know what the other angles are? What does a triangle hold? Remember, 180 degrees. So if you take away 40, that leaves 140 left for the other two angles. So they've each got to be 70 and 70, don't they? And same thing here, 70 and 70 to make, because they're equal. Remember, it's isosceles triangle. So those two angles are equal. So yeah, they have to have the same three angles, don't they? If the top angles, the 40 and the 40 are the same and they're isosceles, that means the two bottom angles are equal. They're both 70. So yes, it's true. They must both be 70. They are, by AA, they've got to be similar. Number 19. Choose the correct. If two right triangles have hypotenuses that are the same length, are the two triangles similar? So if you have one right triangle and another right triangle, they're both right triangles. Well, here, let me make them look different. We're going to basically see the answer to this is no, because one could be like 3, 4, 5, and the other could also have 5, same hypotenuse, where these are not 3, 4, 5. Does that make sense? So those are not similar. Right? They're not the same shape. They're both right triangles. They both have a hypotenuse that's 5, right? The side opposite the right angle. They're both right triangles. They both have a hypotenuse that's 5. But they're certainly not similar. They're not the same shape, right? This one has, these two sides are the same. He's an isosceles right triangle. Maybe I didn't make him good enough there. His top and his bottom are the same, whereas these two are not the same. So one's not just a big version of the other. No, one could be 3, 4, 5. The other could be isosceles with a 5. So no, that's not going to work. Let me go down to 20 down here. How are side, 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 and side angle side similarity like side, side, side angle theorems for congruent? And how are they different? How are they similar? How are they different? Well, basically it's B here. Both theorems relate lengths of sides in two triangles. In the similarities, sides must be proportional. In the congruence, sides must be congruent. So that's what's true there. Let's go to 21. Arturo, some student possibilities here. Arturo writes that triangle ABC is similar to triangle TRI. Betty writes it this way. Who is correct and why? Who is correct and why? So if you're going to say triangle ABC, similar, that little squiggle means similar. similar to triangle. Now, you have to match them up, right? A is the 68-degree angle. That has to go with what? T, doesn't it? You got to start with T, and then comes, right, A has to go with T, and then B has to go, what's B? B is the blank one. B has to go with R, and then C is the 61, that has to go with I. TRI, oh yeah, so it's this way, it's Arturo. So Arturo is correct because A corresponds with T, right? A with T. And C must correspond with I. Correspond with I. T corresponds with I. Arturo. There we go. Nope, I'm not making that very nice there. All right, on we go with number 22. What's happening down here on 22? Bob says that if each right triangle has an acute angle with the same measure, the triangles are similar. So if you have a right triangle, and then like you have another, let's say right triangle, okay, and they have an acute angle that's the same. So say this has got like, I don't know, 30-degree angle here, and this has got a 30-degree angle here. Do they have to be similar? If you have two right triangles that have one of their acute angles, angle less than 90, the same, do they have to be similar? Well, yeah, of course, huh? This triangle and this triangle have to be similar because they have two angles the same. Therefore, the third angles have to be the same, and the two triangles are similar. So, yes, Bob, answer C. Bob is correct. The right angles have 90 if the triangles have an acute angle with the same. They have two congruent angles, and by angle similarity, they are similar. There we go.